Next up, we've got some more considerations of enthalpy to look at. All right, so first, when we look here, enthalpy that's transferred out of our reactants is exothermic, and we get that negative delta H. Transferred into products, we have our endothermic positive delta H. So here's a couple of examples. Now, interestingly enough, most endothermic reactions are not what we call spontaneous, meaning that they don't happen without outside influences causing them to occur. There are cases where they are spontaneous, but a lot of them aren't. So one very common spontaneous endothermic reaction are cold packs. So if you've ever used a cold pack, you have to press on it to break a seal. And so what happens is it breaks a seal between the two reactants. That seal is broken, and now the two reactants can mix. This reaction inside the cold pack is so endothermic that it sucks so much energy in from the surroundings that it gets very cold. And so remember, you are the surroundings. And so what you feel to the touch is something that's very cold. So that's how our cold packs work. Our Bunsen burners, that's an exothermic process. They're giving off heat, okay? And so remember, delta H, it's the state function. It doesn't matter how we got there, okay? All right, now, when I look here, if I take the same reaction and I simply reverse it, all right? So I simply reverse it. All I do is change the sign of delta H. So if I take water and I split it up into its constituent elements, I get 241.8 kilojoules per mole of water, okay? If I take my constituent elements and I combine them, now it's negative 241.8 kilojoules, okay? It's also proportional to the amount of substance that's undergoing change. So I mentioned that we do this weird thing where we put those 1/2 in front of oxygen, so that way we can balance to 1 mole. Well, let's say I balanced it traditionally, all right? So this one is balanced to 1 mole. This is a traditional. Where we've got 2 moles of water. And so what happened to delta H? Well, we had to double it because now instead of dealing with 1 mole of water, we're dealing with 2. Because remember, the delta H of reaction is that kilojoules per mole, okay? Now, the physical state is important. So notice here, I have gaseous water and I have liquid water, okay? So the gaseous water, same thing we've been looking at, this 241.8 kilojoules. But now that I go to liquid water, I get 285.8 kilojoules. So the difference is gas or liquid. So why is the liquid more energy? What do you think? Well, in order to do these reactions, we have to get to that gaseous state. And so the liquid has to go to a gas, and then the reaction proceeds. And so we get more energy because we have to do that phase change first. Okay? And then remember, enthalpy is a state function, same regardless of path, so path independent. And then usually when we look at enthalpy, we're defining it standard state. So 25 degrees Celsius and 1 atmosphere. So these are typical room conditions. Give or take a few degrees. We know sometimes it gets really cold in labs, or sometimes it's warm when it first starts the air cycling. Okay, but those are our typical room conditions. All right, so these are going to be really important because now we're going to start manipulating our enthalpies in different ways. And that state function part of this is really, really important because that state function allows us to look at enthalpy in different ways and to consider different methods for calculating our delta H of reaction based on different types of information that we know or don't know. All right, so that's coming up.